kids' paddle.
How are y'all today?
There are like certain stories about.
I just want to make an announcement here. I posted this on D2L. If you're interested in transferring to CU, there's some information here about visiting the campus Friday, November 8th from 9 to 3 p.m. And so there's a carpool from our campus to that campus, but there's also this agenda for what they'll be doing that day if you're interested. If you are interested, I brought a sign-up sheet. If you want to sign this during break or whatever, if you need a chance to think about it and then want to attend, just send me an email and I'll forward your information along. Just if you're interested in that. I know we missed a day, so we did miss a couple of sections. We're a couple of sections behind now, which we've got what today? Tuesday, next Tuesday, and then next Thursday should be our review. So I think we'll end up having to omit some of our sections from chapter 4, and I'll let you know what those are, but I'll unassign the homeworks and make sure there's no quiz problems on sections that we omitted, but that's kind of where it's at right now. With that being said, we're going to go ahead and finish 4.4, where we're graphing functions, and then we're going to start 4.7. I brought extra notes from 4.7 because I realized most of you probably didn't print that out. So I have some of those if you want to fill those out as we go. But yeah, and I think, if you have any homework questions, just email me, or we can wait till review day to talk about those. But right now we are pretty far behind and we've got to cover some material, so.
We're still in 4.4?
We're still in 4.4, right? We started off with this example where we're graphing this rational function based on various information, and we found the domain, the vertical asymptotes, the behavior near the vertical asymptotes, the end behavior, and we were going to state the intervals of increasing and decreasing in local extremes. So if you've been doing the homework, hopefully you have. You remember that to find intervals of increasing and decreasing and any local extrema, that we have to use the first derivative and test on that number line for the first derivative. So the first derivative was given to us. Let me write this down. So since we're given that, let's save a little time. So there's our first derivative. And what do we need to do to determine this stuff?
You need to
Set the derivative equal to 0.
Yeah.
And what else?
Find where it's undefined.
Find where it does not.
Where it's undefined, right? So critical points where the first derivative is 0 and where the first derivative is undefined. Let's see, what do we have? Okay, so when is our first derivative equal to 0?
F is never.
Never, yeah.
Right, so our first derivative is this quotient, and our quotient is 0 only when the numerator is 0. Okay. So -3 is never 0, x squared plus 1 is never 0. So we would get imaginary solutions to this if we were to solve it out all the way. But the fact is that the first derivative is never equal to 0. So we don't get any critical points there. We got to be mindful of our domain was all real numbers except for 1 and -1. Okay. And then our first derivative is undefined where?
At x equals 1.
At x equals 1. Do y'all agree?
And negative 1.
Yeah, it's undefined. Since we're dividing,
Yeah.
it's undefined when x squared minus 1 squared is equal to 0. And x squared minus 1 is 0 when x is plus and minus 1. Oops. When x is positive or negative 1. So are those critical points?
Yes. Oh, no, they're not.
No, because they're not in the domain.
Right. Those 2 points are not in the domain of the original function.
Right.
But in the original function, what's happening there at 1 and negative 1?
It's asymptotes, right?
Yeah, we've got asymptotes. So even though we're not coming up, per se, with any critical points, we'll just label this as not in the domain. So even though we don't have anything like critical points-wise to put on our test line for the first derivative, we do know that the first derivative is not defined at 1 and negative 1. So is the function. So really the function having asymptotes there does give us a means to split this up. We've got 3 different regions.
It's not.
Yeah, but remember to determine where the original function is increasing or decreasing, we have to test on the derivative, not the function itself. So we're labeling this f prime, and we're just going to pick our test points to the left of negative 1, in between negative 1 and 1, and to the right of 1. So I don't know, maybe that's negative 2 to 0 and positive 2. And we're evaluating our first derivative at those locations. And really just we're after the sign. So we have our f prime evaluated at negative 2. Notice f prime, the quantity x squared plus 1 is a quantity that's always positive. And the denominator is always positive in the first derivative, right? So when we look at the first derivative, it's negative 3. The things in parentheses don't contribute to the sign because they're always positive, regardless of what you plug in. So in fact, the first derivative is always going to evaluate to what kind of number? A negative number, right? Because I'll just write it out here. Our first derivative for any x is this negative 3 times a number that's always positive over a number that's always positive. So regardless of what you plug in, you're going to have negative 3 times some positive number. So the first derivative is always negative. This is negative, this is negative, this is negative. And what does that mean about f of x? It's decreasing. More specifically, we should say f of x is decreasing on its domain.
Yep.
Yeah, I'll just keep going here. We'll have to start another page. So the sign chart for f prime tells us f of x is decreasing on the interval negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity, or decreasing on its domain. So do we have any local extreme values? No. How do we know we have no local extremes?
Never equals 0.
your sign for the first derivative in the first derivative test, it never changes from negative to positive.
Right.
It's always negative. If it changed sign once, we would have a p go across.
Yeah.
But since it never changes
It's just
sign,
going in the same.
Exactly.
it's always somehow going.
The first derivative never changes sign, right? We don't change from negative to positive or from positive to negative. Therefore, there are no local extremes. Is everybody okay with that? If the function itself was increasing and then decreasing and then increasing again, then we have a max and a min. But again, those things only, local extremes only occur when a sign changes across a critical point. All right, so we'll say that as well. F of x has no local extreme values, meaning no local maximums or minimums. So f of x is always decreasing. Anyone have any questions on this? Okay. Start another page. I forgot what part we were on. This was part D. So part E, we're going to state the intervals where the function f of x is concave up and concave down. Also, the location of any inflection points. Okay, so intervals of concavity and inflection points are determined by what?
Second derivative.
The second derivative. So we're going to find, or actually we were given the second derivative, so we're just going to write that out. We were given the second derivative is 6x times x squared plus 3 on top, all over x squared minus 1 cubed on bottom. So same procedure, we need to determine where the second derivative is 0 and where the second derivative is undefined. Clearly, we can see that it's undefined once again when x is 1 and negative 1. To no correspond to asymptotes on the original function. So if you've got a rational function that has an asymptote or asymptotes, those things always carry down to subsequent derivative tests. There's no way to remove those from the original function. So when you're drawing out your test for your first or second derivative or third derivative or whatever, you want to put those asymptotes there because the function has to be split up by those asymptotes, regardless of if you get any critical points. Does that make sense? Your asymptotes are always cutting your plane, regardless of what derivative you're talking about. So for instance here, we've got our asymptotes where the second derivative is undefined. Our second derivative rather is equal to 0 when x is equal to what? 0. Again, our quotient for our second derivative is only 0 when the numerator itself is 0. when 6x is 0 or when x squared plus 3 is 0. And of course, x squared plus 3 is never 0. 6x is equal to 0 when x is equal to 0. So is x equal to 0 something we're including in the second derivative?
Yes.
Right, because the domain of the function was just everything but 1 and -1. So we're including this value when we test our second derivative. I mean, we're not directly including the 1 and -1, but it sort of manifests how it did in the first derivative test. We're going to draw out a number line for our second derivative. We have our asymptote here at -1 and at 1. But we're also coming up with x equals to 0. So we're going to have this here. So we actually now we have 4 different intervals we have to test for concavity. So we have to test here, 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 and here. Again, concavity, we're testing in the second derivative. So we'll just do this here, -2, maybe -1/2, +1/2, and +2 in our second derivative. Let's see, our second derivative was yeah, so I guess our second derivative wasn't as friendly as the first as far as like what's positive and what's negative. At the very least, we can say that the second derivative, that x squared plus 3 is always positive regardless of what we plug in. The x squared minus 1, since it's cubed, could be positive or negative. So maybe we'll just look at 1 or 2 of these. F double prime at -2. So F double prime at -2. What would that give us? Positive or negative?
Negative.
Yeah. Do y'all agree? Negative? Okay. But a -1/2.
Positive.
Positive? What do y'all think? Yeah, so the 6x is negative because it's a -1/2. So negative times a positive on top. And then we've got a quarter minus 1, which is a negative number squared, or cubed rather, which is another negative number. So you got a negative times a positive over a negative. It's positive. How about at +1/2? It's negative, top's positive. So we've got a positive times a positive, but the bottom is negative. So that's negative. And then at +2, positive as well. Positive times a positive over a positive. Again, for these rational functions, for polynomials, don't just assume that your sign chart's going to alternate. If it does, great, but it doesn't always alternate. You really need to test each one of these values in the first or second derivative. Okay, so that sign chart for F double prime tells us what?
Concavity.
Yeah, our concavity. So we've got the fact that our original function is, I'm going to abbreviate this, concave down. on the interval from negative infinity to negative 1. And make sure when you're using these sign charts that you're clearly marking the critical points and distinguishing them from your test values. Again, one of the major issues I see is people saying, okay, this f of x is concave down from negative infinity to negative 2. So you never go up and stop at your test point. You always go up and stop at your critical point, or the zeros and undefined places of your second derivative. And it's concave down as well from 0 to 1.
Concavity direction.
Okay. Just kind of moving this. And let's see, concave up
So
on the interval negative 1 to 0, and from 1 to infinity. Are there any inflection points?
Or water runoff. Or the water runoff.
Include 0 on that?
Huh?
0 or inflection?
Concave down.
Yeah, the only one we can include, we see that it changes signs through negative 1 and positive 1, but those are vertical asymptotes. There's really nothing on our graph at those locations. The only place that makes sense to change signs is there at 0. So we have an inflection point. When x is equal to 0, the point on the graph is 0, comma f of 0. What was our original function? Our original function was 3x over x squared minus 1. So inflection point at the origin. Does anyone have any questions? I hear some whispers. We'll make sure that we're all.
Can we go back to the graph and explain why the original inflection point on this one?
Because at 0 we change signs. Second derivative goes from positive to negative, so it changes concavity there. It's concave up and then it changes to concave down when you move across 0.
So an inflection point would be where it's defined there and it changes concavity?
Right, right. You couldn't have an inflection point like on a graph where the function's undefined. So like even though the second derivative would go from negative, let's draw this out. The second derivative would be negative and then positive. We wouldn't say that there's a point of inflection here because f of x isn't defined there. But the function is defined at 0. So it's changing, well, it's reversed that situation. But the idea is analogous to the first derivative. When the first derivative changes sign, you've got a local minimum or a local maximum. The analogy with second derivative is when it changes sign, you have an inflection point. Is everyone clear on that? Like, we don't have inflection points at the asymptotes because there's nothing there. So I don't know, I didn't really claim that this was a better way to graph. It's just another way to graph. It's pretty lengthy.
It gets you a better graph.
Yeah.
It's not easier.
It's not, yeah, maybe it's not easier, but yeah, all right. Any other questions or clarity needed on that? Okay. So really what we have now is the first and second derivative. We can put that together to give us kind of a picture of like how the function is shaped. But we have to be mindful of our vertical and our horizontal asymptotes as well. So let's just see here, put the first and second derivative together to give us a picture of f of x. So this is where we would put all of our values on the first and the second derivative, where those were 0 or undefined. If we want to make this larger too, it doesn't matter. But basically, we're splitting the function up in terms of the information we got from the first and the second derivative. From the first derivative, we saw that the function was always decreasing. So in each one of these intervals, f of x is decreasing. No local maximums or minimums. From negative infinity to negative 1, the function was a concave down. From negative 1 to 0, it was concave up. From 0 to 1, concave down. And then from 1 to infinity, it was concave up. Okay, any questions on that? We're just basically you're going to take that sign chart for the first and second derivative and just superimpose them together on top of one another. That way we get a clearer picture of where the function's increasing and decreasing, concave up and concave down. And then so each piece we could draw according to that first page. The function is concave down and it's decreasing. So decreasing just means that as we move from left to right, that the function falls. So we've got, something like that is decreasing. And then since it's concave down, it's shaped sort of like that. Then it's decreasing again and concave up. So decreasing, falling from left to right, but this time it's concave up. Decreasing and then concave down. Like, we know that these two things aren't connected, right? Because we've passed through the asymptote. So these are two separate pieces. However, 0 is included in the function. So as we go from decreasing and concave up to decreasing and concave down, we're going to fall again from left to right and then make this concave down. And then again, we're passing through this asymptote, so these two pieces won't be connected. That last piece, however, though, is decreasing and concave up. So again, falls from left to right, decreasing, and then it's concave up. So, that's the basic shape of our graph. Where those pieces go, we then have to kind of use our information about where the asymptotes are. I'm not saying that this is like a contiguous piece of the graph, right? It's just in each region, we know how the function is shaped. Does anyone have any questions on the pieces? All right, so then when we actually draw a better graph, this here. And we had our horizontal asymptote at, was it y equals to 0, right?
Yes.
Oops. So this is our horizontal asymptote. So we know that first piece, if it's shaped like this, where does it go? Over here. It has to be here, right?
Yeah, there.
It has to be there. The second region in between our asymptotes was sort of like this backward cubic function. Remember, we have an inflection point at the origin. There's a point on the function at 0, 0. Decreasing in concave up, and then it's decreasing in concave down. And then our final piece was decreasing in concave up. So does it go above or below the horizontal? It has to go above. Decreasing in concave up. No local extremes. There's really no other points of interest to find. So that's it. That's, you know, all of that information to give us this graph. And I know this is time consuming. I would at least recommend on the homework that as you vary the functions, maybe a polynomial, a rational, exponential, or something to that effect, that you at least attempt those this way. And if you're at a point where you're comfortable in how this works and you're pressed for time, then maybe you could take a shortcut. But there will be one like this on the exam. So I wouldn't recommend taking any shortcuts until you're very convinced that you know how to do this stuff and that you can get an accurate picture. So does anyone have any questions on this?
You just do the same thing with both derivatives, right?
Yeah.
Set the top to 0, find the undefined.
Yeah.
Bada bang.
Yeah, in a nutshell, that's it, right? Yeah. Any other questions or comments on 4.4? All right. So who needs notes for, or skeletal notes for 4.7? So if you wouldn't mind keeping your hand up, so it's 3.
So does that mean right now we're trying to first courses? So maybe it was never the intention to do it. That's fine.
Whatever's gonna happen is gonna happen.
I hope that the sections that we missed, for those of you that go on to Calc 2, if we're not able to come back to them at some point, it should not be detrimental at all. There might be a couple of theorems they mention where they're like, oh hey, you remember the intermediate value theorem? This is how we prove this following theorem, and you're going to be like, oh, I don't remember that, but it's not going to be something that's heavily relied upon. So 4.7 deals with limits again. So we're back to another technique to evaluate limits with L'Hopital's rule. L'Hopital. And I think it's extremely useful. In fact, most limits that don't evaluate could I would default to this method before I tried anything else. But we're dealing with limits of the form. There's two forms. One is 0 over 0, and the other is infinity over infinity. With infinity, we don't really care about the sign. It could be positive over a negative over a negative, whatever. It's any form of infinity over infinity. And just a reminder of the notation, these two things arise in the sense of a limit. Of a quotient. So when we write 0 over 0, we're not saying 0 divided by 0. We're saying that the numerator approaches 0 and the denominator is approaching 0. Or the numerator approaches infinity as the denominator approaches infinity. Okay. And these two limits are called indeterminate. Indeterminate forms. And its name is as it implies. 0 over 0 or infinity or over infinity is not something that you can directly determine. It's not 1, it's not infinity, it's not 0. These are called indeterminate forms. Indeterminate forms, let me abbreviate this. Indeterminate forms. And indeterminate forms can have any value. It's really up to us through this process of using L'Hopital's rule to determine what that value is. We're not saying that when we evaluate this limit of f of x over g of x, that it can have any value. If the limit exists, it has one specific value. But in general, these indeterminate forms can take on any value. Okay, so these are the two forms that we're reverting back to. These are the two forms that you have to have present when you're evaluating a limit to use L'Hopital's rule. If it's not 0 over 0 or infinity over infinity, you have to rely on other methods. So as the theorem states, I think this one's for 0. Oh, it's for both. But as the theorem states, L'Hopital's rule says that if you end up with an indeterminate form for this limit, 0 over 0 or infinity over infinity, then that limit we can compute by looking at the derivative of the numerator divided by the derivative of the denominator. And notice that the confusion typically at first arises in the fact that we're not actually computing a quotient rule for this f over g, right? We're not saying it's g times f prime minus f g prime all over g squared, right? It's just take the derivative of the top, divide that by the derivative of the bottom. So don't confuse L'Hopital's rule with the quotient rule to take a derivative of a quotient. So unfortunately, since we haven't covered 4.6, it really can't do much in showing why this is true. But it is based on the idea that is discussed in 4.6. Okay, so that's L'Hopital's rule, and I would prefer that when you apply L'Hopital's rule that you indicate that by putting an h over the equal sign. So whenever you take the derivative of the top and the derivative of the bottom to evaluate a limit, just put the capital H over the equal sign. It's not a notation our textbook uses, but many other textbooks use it. And that way we're all clear as to when we've used this rule to evaluate. Okay, so for instance, do y'all remember this limit here, the sine x over x as x approaches 0? We saw that limit when we were deriving the derivatives for sine and cosine. And I think that was 3.5, and in section 3.5 we just said, hey, this limit is equal to something, right? We just gave that as fact. There was a geometrical kind of proof in the textbook. But now we can go back to these types of limits and evaluate them a lot more easily. So let's say we forgot what this limit was actually equal to. The first step when you look at a limit is always just to evaluate the limit. So as x goes to 0, I'll just write here, this is our direct substitution step. X going to 0, the top sine x approaches 0, and the bottom approaches 0. So since it's a form 0 over 0 that applies to, that L'Hopital's rule applies to, then we're just going to compute this limit by computing L'Hopital's rule. So we're going to take the limit as x goes to 0 still, but we're going to compute the derivative of the top. Derivative of sine is cosine, and divide that by the derivative of the bottom. Derivative of x is 1. And then we try to reevaluate the limit. As x goes to 0, what is this limit?
So on an exam, if we were to do this, to kind of explain our reasoning as to why we're doing this, we would have to put the equal sign with the h over it
Yeah.
to indicate that we're using this rule.
Right.
Okay.
Right, yeah, so on the instructions on the exam, I'll say, evaluate these limits and clearly indicate when you have used L'Hopital's rule, and just the h above the equal sign is sufficient. If you wanna write next to your step, hey, I used L'Hopital's rule to get from here to here, that's fine, but I think it's a lot more compact and neat just to put the h above it. As long as you indicate to me that you've used it somehow, I'm okay with whatever. But then we can evaluate this limit directly. So the limit as x approaches 0 on sine x over x is equal to 1. Does everybody see how that works? Are there any questions? Is there anything else? Yeah, this one. So example 2, we really do have a really efficient way to evaluate this limit. What should this limit turn out to be? 3. Right? We have a polynomial over a polynomial. All we have to do is look at the leading term 3x squared over the leading term x squared. And that's just going to simplify to 3. Again, say we forgot that. We evaluate this limit directly, and what do we get? Yeah, the infinity on the top, infinity on the bottom. So it's one of the two forms. We apply L'Hopital's rule. Again, we take the derivative of the top and divide that by the derivative of the bottom. So we have 6x minus 1 over 2x. Okay, so as x goes to infinity, 6x minus 1 over 2x goes to what? Approaches what? 3? Yeah, again, if we're not seeing the leading term thing over the leading term, then we evaluate this limit again and get infinity over infinity. And so yeah, we've got this second form is still a form that L'Hopital's rule applies to. So we can apply L'Hopital's rule again.
6 over 2.
Yeah. So we're going to apply L'Hopital's rule again. As x approaches infinity, derivative of the top is 6, derivative of the bottom is 2. And then when we write equal, we're just writing, algebraically equivalent to the limit as x approaches infinity on 3, which of course is just 3. So I don't think it's as efficient to use L'Hopital's rule in certain instances, but if you forgot, then you arrive at the same conclusion everybody else arrived at. There is no limit to how many times you can apply L'Hopital's rule. As long as it's 0 over 0 or infinity over infinity, you can keep applying it indefinitely. Like if we started out with 3x to the 8 over x squared to the 8th, right, we would eventually whittle that down to 3 over 1. But again, the most important thing to realize when we're using this rule is that your limit has to be of the form 0 over 0 or infinity over infinity, and you have to do the derivative of the numerator divided by the derivative of the denominator. Does anyone have any questions? All right, so the limit as x approaches -1 on this function here. Infinity over infinity, what do y'all think?
Something over 0.
Something over 0.
0 over 0.
Something over 0, right? Well, we've got to make sure that it's actually 0 over 0. Clearly, we can see the denominator is 0. But what happens if we plug -1 into this? And I don't know. And let's say we've got some number like -4. What would the limit be if it's -4 over 0? Negative infinity, right? So I'm just saying, like, these types of limits here, or these types of limits here, we have other means to evaluate those, because L'Hopital's doesn't apply to those. Those limits are infinity or 0. So you still have to remember that stuff. It's not like we get L'Hopital's rule and forget everything about limits. It's not, I guess it's not that convenient. So what does the top evaluate to? 0? 0 over 0. So normally in this sense we would say, all right, well, our only choice is to try to factor this 5th degree polynomial on top, and hopefully a factor of x plus 1 will cancel out, right? So I assure you probably don't want to do that. So we can say, all right, well, we've got a form 0 over 0. Let's just apply L'Hopital's rule to this, instead of trying to like factor and simplify. So the limit as x approaches -1, derivative of the top, 5x to the 4th plus 8x cubed plus 3x squared plus 4x plus 4, all over the derivative of the bottom, which is just 1. And clearly we can evaluate that limit. So as x approaches -1, that function approaches a number. That's right.
One moment.
Winning.
Hey, am I wrong though?
So you've got a 5 minus 8 plus 3 minus 4 plus 4. 0. Yeah.
What?
Right. That limit is 0. We've seen 0.
No, you can't.
So these 3 examples show that in this instance, the form 0 over 0 was actually equal to 0. The previous example, 0 over 0 is equal to 1. And the second example, infinity over infinity, was actually equal to 3. So that's what we mean by it can have any value.
And you couldn't do it again because then the bottom wouldn't equal 0, which would make it undefined.
Right, yeah. So that's the thing with L'Hopital's rule. If you apply it, you simplify the function before you reapply it. So if we simplify this function and evaluate this limit, it just comes out to be 0. It's not 0 over 0. So you wouldn't apply L'Hopital's rule again to this limit because it's not 0 over 0 or infinity over infinity. So you should reach a definitive stopping point when you're applying this rule. Maybe we should denote here that when you apply L'Hopital's rule, the steps are always consistent. So you apply, L'Hopital's rule. Then you always simplify. Then you reevaluate. And if you have to repeat the process, that steps 1 through 3 repeat. So it's always, you always want to simplify after you've done L'Hopital's rule. S-I-M-P-L-I. Simply, that's right. It's hard to talk and write sometimes. I'm not good at it. S-I-M-P-L. Yeah.
There we go.
Did it.
Calculus.
Thank you. Yeah. That was one of the joys of finally just doing math classes. I never had to write another paper.
That's what
I'm so happy.
Half of the reason.
It's glorious.
Same.
All right, so just keep that process in mind. We will later. We will look at an example where L'Hopital's rule does apply, but it doesn't actually give you any information. So, there's always these caveats. We're going to cover all of them. And by the way, on this function here, if we were to graph this function, what's our limit telling us is happening on that function? Right, which means what happens as x approaches -1, y approaches 0. What is that on the graph of this function?
A hole.
It's a hole, right?
You could factor it out of that.
Yeah. You could have factored it out, right? But the function here, all of this stuff over x plus 1, is undefined when x is -1. And then, so the question is it an asymptote or is it a hole? Well, if it were an asymptote, what would our limit came out to be?
Infinity or negative.
Infinity or negative infinity. However, we're approaching a place in the function where it's undefined, and we're getting a finite number. It has to be a hole or a removable discontinuity. Yeah, I don't know what this is. Negative. Zero. Negative. So let's just say right here, -1. The y value was 0. Whatever our function's doing, it's doing something like this. It keeps going. So you've got a hole in that graph. That's it. All right, why don't y'all try example 4.
I'm not looking previously in my notes for knowledge that completely grew out of my head as soon as we got the program. Did you really grasp that? I love that. Beautiful. Great math.
Special, like the graph is like if it goes 2x plus 4 plus x cubed plus 2x squared plus 4x plus 2 all over.
Let's grab that by hand.
Done.
It's secant 2x. I
Oh,
just
that's for the
Which is, so 1 over
The upper, yeah, because it's changed in the function.
I thought that was a constant, so you can just pull it out.
No, that can't be.
we would say,
Because four is something that
we don't do
So it's secant squared. Secant squared. Secant squared.
So, wait, hold on. Maybe, I don't know, but like, why are you pulling the 4 and the 7 out? Isn't it the,
So the derivative of secant squared, tangent of AX, times X, is secant squared AX times the derivative of AX.
oh, so you're just, well,
So I'm just
okay.
moving the AX.
Yeah.
By changing it, yeah.
Yep, you're right.
But then when you do it
Because
that.
I was about to argue with you and tell you literally the same thing, but what you just wrote as opposed to what you did just now. So, that's cool.
Yeah, we just moved it out.
Yeah, that's fine.
because like, with changes.
How do you evaluate secant squared as a weird number?
Yeah. The derivatives with rotations.
Secant squared is
I know, right?
That's where
All the way around the book.
No, you just do like one over.
Yeah, and I mean, I think this honestly should be earlier in chapter 4, because a lot of the graphs you end up with, you have to use this to determine like where that point is or that
That
goal
you,
is.
but
It's pretty much after
I'm just gonna notice like every time we
That's really cool.
especially what was it?
So, tell me if you get the same thing as me, okay? For the numerator.
Still have like do some like
wait,
Yeah.
a lot of it requires you to take especially 4.9.
I got 1. Oh, wait, that's, which means that,
There is some
For sure.
should look like.
Yeah.
So it's a little bit calm.
is this correct?
Yeah.
4 seconds.
oh, okay, yes.
Yeah.
Oh, because cosine 0 is just 1. Oh, that makes sense.
All right, again, with any limit, just make sure you're evaluating it first to see what you come up with. If it's something that L'Hopital's doesn't apply to, and you apply it anyways, you're gonna get misinformation. So please always evaluate limits directly before you just jump into doing L'Hopital's rule. The tangent of 0 is what?
0.
Yeah, so the top and bottom approach 0. And we apply L'Hopital's. So we take the derivative of the top. What's the derivative of tangent 4x?
4 secant squared 4x.
Yeah. With a chain rule. You get a similar situation on the bottom. 7 secant squared is 7x. So we've applied L'Hopital's rule. There's nothing we could really simplify. The two different arguments of secant keeps us from canceling. So we applied L'Hopital's, we simplified, and then we reevaluate. So as x approaches 0, what does secant approach? 1. So this limit is now, we can evaluate this limit. It's 4 times 1 over 7 times 1, or 4 over 7. Again, on the graph of tangent 4x over tangent 7x, what's happening?
Is
there's a hole. Where at? 0, x approaching 0. 4/7, right. So here we go.
Whoa.
Because then,
Yeah.
even if you have a quotient over.
And notice, like, this function here, the computer defines it. Remember the intermediate value theorem? It plots all intermediate values, just assumes it's continuous. We know that it's not. Once you get here, and you've got to hover your mouse over it, it'll tell you it's 0 undefined. And that's not very helpful, because what is the y value we're sitting at? Well, it's 4/7. All right.
And it doesn't look like it's undefined there on Desmos.
Yeah, and any graphing software would probably, that I'm aware of, wouldn't show you that there's a hole there. I mean, the computer really can't show you, right? Because a hole is just a deleted point, and a point has no dimension. So like we could zoom in on that forever and never actually see that single point has been removed, but it has been. All right. I'm just going to skip this. This was sort of our justification of why L'Hopital's rule works, but we didn't do 4.6, which if we don't cover 4.6, you're not responsible for any of it. But just so our notes doesn't have this big thing hanging out with nothing, we'll just say C 4.6 linear approximation.
Yeah,
That's one of the ways to show that this works is through that section. And section 4.6 is really just saying, hey, if you've got a function, like in chapter 3 we worked on, here's a function, what's the equation of the tangent line at this point? And you came up with like y equals mx plus b. Like 4.6 is just using that tangent line to approximate functions. So that's really all that was. If we have time, we'll go back to that, but. Okay, let's write related indeterminate forms, and we'll take a break and then look at the related indeterminate forms. And what we mean, related indeterminate forms means that all three of these are related to our 0/0 or the infinity over infinity. They're not directly 0/0 or infinity over infinity, but they are related, which means through certain techniques we're able to turn something back into these two things. Okay, the first one that we'll look at is 0 times infinity. And again, that's 0 times infinity or negative infinity. And that's coming from computing a limit on a product. Where one factor is approaching 0, the other factor is approaching infinity. And so like that's what that's showing is it's one factor is getting smaller and smaller, the other factor is getting larger and larger. What actually happens to the product? Does the infinity win out? Does the 0 win out? Are they comparable and you get some finite number? That's why 0 times infinity in the sense of a limit is indeterminate. So 0 times infinity is 1. The other one is infinity minus infinity. And of course, that arises from a limit that has subtraction in it. What if your limit was you ended up with infinity plus infinity? What would you say the limit is? It's infinity, right? But why infinity minus infinity? Why is that indeterminate. Well, infinity is not a number, right? So these aren't the same. They're not growing to the same value, right? We're just saying that this function is growing arbitrarily large to some arbitrarily large number, and g of x is growing to another arbitrarily large number. So infinity minus infinity in the sense of a limit is not to be interpreted as some large number minus itself. It's just some large number minus another large number. Whichever one of these numbers or functions would be larger would determine, like, that's your infinity, right? Like, if the first one's larger, then it's a large positive minus, so you'd have a large positive. Or if the second one was larger, it'd be a large positive minus an even larger negative, which would be a large negative number. But usually it's neither one. Usually it is some finite number. Okay, and then the third scenario. There's three of them. It's 1 to the infinity, 0 to the 0, or infinity to the 0. And so these are arising from limits. Of the form f of x to the power of g of x. And what we'll see when we actually get here, we'll see that these limits really are the first scenario, where it's 0 times infinity, but we have to rewrite them first. Okay. So you might remember how we've rewrote those things to take their derivatives. That's how we rewrite them here to evaluate their limits. But anyways, those are the three forms that we're going to look at after the break. And each one of them has a different approach in how we get them back to 0 over 0 or infinity over infinity. So there's really three different processes.
Does that apply to all three rules or just the bottom one?
Which, like, this
Yeah.
in blue? Yeah, it's for the third scenario.
Okay.
Yeah. All right. Yeah, so we'll look at those processes after break. Does anyone have any other questions or comments for now? All right, so we'll take a break.
Oh, if you want to fix your services, it sucks. Get it 95.
I haven't thought about it.
It's awful.
Yeah.
It's uncomfortable.
Yeah.
But I used to travel.
So, the first indeterminate form is limits of the form 0 times infinity. And you've got to think about whatever scenario you come up with. In order to apply L'Hopital's rule, it has to be 0 over 0 or infinity over infinity. So when we have a product of two functions, or a product that we need to turn back into a quotient, how do we do that? All of these evaluations, or getting back to something L'Hopital's applies directly to, are just algebraic techniques. So how do we rewrite a product as a quotient? How would we rewrite f times g as an equivalent quotient? So how would we write 2 times 3 as an equivalent expression involving division, not multiplication?
2 2 divided by 1 divided by 3.
Okay, 2 divided by 1 divided by 3. What do y'all think? Does that work?
It hurts, but I don't like it.
It hurts and I don't like it, but it works.
But it works, right? 2 divided by a third is 2 times 3. Or the other way around, right? And so we'll see an example of why, there's 2 ways to do this. In practice, that's better for us because oftentimes one way of rewriting that might not yield something that gives us any information. Okay. So then what we're saying is that f times g can be rewritten rather as f of x divided by 1 over g of x, or g of x divided by 1 over f of x. And so here, the way we're writing this would indicate that as x goes to a, the function f approaches 0, the function g approaches infinity. So if we rewrite, for instance, the limit as x approaches a of f of x divided by 1 over g of x, where f of x is approaching 0 and g of x is approaching infinity, what do we have here with f of x over 1 over g of x?
0 over 0.
0 over 0, right? Because 0 is on the top, but the bottom is approaching 1 over an arbitrarily large number, which means that quotient 1 over a large number is actually approaching 0. Works the same way with the other one too. So that's now something. F over 1 over g is now something that's of the form L'Hopital's rule applies to. So then we take the derivative of f and divide that by the derivative of 1 over g. Does anyone have any questions on that? So to turn an indeterminate product into a quotient, you simply divide by the reciprocal of one of those factors. So let's evaluate the limit as x approaches 0 from the right on x times the natural log of x. So we first need to figure out, can we even evaluate it? As x approaches 0, factor 1 approaches 0 times ln of x approaches what as x approaches 0?
Negative infinity.
From the right, negative infinity. Okay, so it's an indeterminate product. We then need to rewrite this algebraically. So we're just going to have an equal sign for now. So there's 2 ways to write this, right? Let's look at both of them and see, is one preferred over the other? So what's one way we could write the product x ln x as a quotient?
X over 1 over ln x.
Okay, good. X divided by 1 over ln x. The other way?
It's ln x over 1 over x.
Right, is ln x over 1 over x. So one factor divided by the reciprocal of the other factor. And so, we have 2 things to work with here. Which one? It really just depends on which one's easier to work with, because both of them are valid.
We're gonna have to take a derivative.
Yeah, so let's see what both of these are before we actually proceed. The one on the left, as x approaches 0, what does that limit evaluate to?
So it ends up being 0 over 0.
Right, so it's by direct substitution, it's 0. Again, over 1 over infinity, and 1 over infinity is approaching 0. So that's something we can apply L'Hopital's to. What about the one on the right? By direct substitution, this is what?
It's negative infinity over undefined, right?
Well, close, yeah. So the top is negative infinity over 1 over something approaching 0 from the right. Just like, remember the graph of ln? Looks like this.
Oh, okay.
Yeah. So the denominator, 1 over a smaller and smaller number, is a larger and larger number. So that one's infinity over infinity. So either way we've had this function expressed, either one of those is directly applicable to L'Hopital's rule. So let's look at this one on the right. Since it's infinity over infinity, we're going to apply L'Hopital's rule. So that's equivalent by L'Hopital's rule to the limit as x approaches 0 on the right. Derivative of the top divided by the derivative of the bottom. What's the derivative of 1 over x?
0.
It's x to the negative 1.
No. Okay.
Yeah, negative 1 over x squared. So we've applied L'Hopital's rule, then what should we do?
Multiply by the reciprocal?
Right, we simplify the expression. We wouldn't want to evaluate this again. It's L'Hopital's rule, then simplify, then reevaluate. If we tried to evaluate without simplifying, notice the top is approaching infinity, the bottom is approaching negative infinity. So you would still say, all right, let me apply L'Hopital's rule again. You'd get negative 1 over x squared over 2 over x cubed, infinity over infinity again. So you would always get infinity over infinity if you failed to simplify. So L'Hopital's rule, then simplify. So this simplifies to the limit as x approaches 0 of what?
Negative x.
Negative x. The negative x squared over x. So L'Hopital's rule, we've simplified, then we reevaluate. As x goes to 0, this limit is 0. Which again, what that means for us actually is that the original limit is 0. As x approaches 0 from the right on x times the natural log of x, that limit is 0. Are there any questions on that?
Do you have to put the h on the limit going to negative x?
No, here, this was, we didn't apply L'Hopital's rule. All we did to go from here to here was to simplify
So
this.
simplify it. Yeah, I didn't know if we had to keep putting that on to indicate that.
No, if we're just,
Add use here?
yeah, if you're just doing like an algebraic step, it would just be
Just take
equal.
it out.
Yeah,
Okay.
or when you evaluate the limit directly, it's an equal.
So it's, the h is only when it's directly applied in that instant.
Yeah, when we apply from the previous step, the derivative of the top, derivative of the bottom, that's when we put the h. Okay. So both equivalent forms, this should also give us 0. Let's see how this works out, though. We already said that this x over 1 over ln was 0 over 0. So we would apply L'Hopital's rule to that limit. And so we have the derivative of the top divided by the derivative of the bottom. So what is the derivative of 1 over natural log of x?
It would just be 1 over x eventually.
Oh, wait.
Well, so we've got to take, maybe we'll do this off to the side if we have room. I guess we really don't. We have to compute the derivative of 1 over the natural log. The derivative of natural log itself is 1 over x, but we don't have that, right? We have a quotient rule, or we can use this chain rule if we say it's the natural log of x to the power of negative 1. But either way, it's not just going to be 1 over x. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So remember the natural log of x, quantity squared, is not the same thing as the ln of the argument x squared. So the power property of logarithms doesn't apply to that. We have a minus 1 over x on top and an ln squared on the bottom. Sometimes it's written like a trig function, just to avoid the confusion with the power property. Is everybody okay with the derivative there? Any questions?
Does the 2 go off to, does that make it 2x ln x?
No, because this is really this, and it's not this. Because this right here is this. Yeah.
I'm a little bit confused for a moment. So we had x over 1 over ln x.
Right.
So we take the derivative of the top and the bottom. And when we do that, we have, so the top is going to be 1.
Right.
And then the bottom one's going to be 1 over x.
Right, but so the entire denominator being this function here, though, right? This is our denominator is 1 over the ln of x. We wouldn't want to do L'Hopital's rule individually to that, because L'Hopital's rule says take the derivative of the numerator divided by the derivative of the denominator. So since this whole thing is our denominator, we have to take the derivative of that whole thing.
Okay.
We wouldn't, again, look at it as derivative of the numerator over the derivative of the denominator, again, because the denominator itself is a quotient.
Okay.
So we need the quotient rule there. Yeah. So that's a good point. In most cases, when you rewrite this, function divided by the other one's reciprocal, that 1 over g of x part will be a quotient rule. Or you could look at it as a chain rule if you rewrite it as g of x to the negative 1 power. Okay, so negative 1 over ln squared. Does anyone have any other questions on that? Okay, so L'Hopital's rule here, then we would simplify this. So algebraically equivalent to the limit as x approaches 0 from the right of x ln squared x times negative 1. And then, so what happens here? We've now evaluating the limit as x approaches 0 of x, negative x rather, times ln squared. So did that improve our situation? Now it's virtually the same limit we started with. We started with x times ln x. Now we have a negative x times ln squared. So this route isn't going to yield anything. We're just going to keep getting x's in higher powers of the natural log, which would still be a 0 times infinity situation. So I don't know how you want to say that, but with this process, we don't gain any information. That is, the limit is always of the form 0 times infinity. So there we would just keep going around and around and around. You would never determine anything precisely. But the other way of writing it, we did determine precisely that that limit was 0. Yeah.
So maybe this is a silly question, but why is it if we have, you know, ln x is undefined, but we have it multiplied by essentially 0, so why does multiplying this function by 0 not make the undefined part negligible?
So a valid question. There's really two ways to think about it. So if I say take 0 and multiply it by something undefined, does that make any sense? Like 0 times something that's not defined, like 0 times the ether is what?
Whatever you want it to be.
It's still undefined. Yeah, it's still undefined. 0 times something that is defined is equal to 0, right? But 0 times something that's not defined is something yet that you can't define, right? The other way to think about it is all this limit initially was saying was that as we get closer to 0 from the right, this factor x gets closer to 0. So this factor is getting smaller and smaller, while the natural log factor is getting larger and larger in the negative direction. So then the question in that respect is, okay, well, is this one approaching 0 fast enough to make all of that 0? Or is this thing getting large enough, fast enough to make everything super large? Like 0.001 times 5 trillion. Or is it really 0.001 times 5? So that's kind of what's happening. In the context of a limit, it's not that we're multiplying something by 0. It's just we're multiplying something by a smaller and smaller number. Does that make sense? So here's x ln x, and we came up with this limit to be 0. So we do know that our work here shows us that as we approach 0 from the right, the y value approaches 0. In other words, there's a point at the origin at 0, 0. So this thing does say 0, 0, but it's not really accurate. This function x ln x is not defined at 0. So you really should have a hole right there. So whatever they're using to determine that clearly has limitations. Oh, we ran out of room. This should be all right when you look at the notes. And of course, we're avoiding having to graph stuff, so that's just a visual verification. Yeah.
Is there any way of knowing like which is better to put on top or bottom to like make sure that we don't end up with something that's going to keep repeating? Yeah, like
Yeah.
your F over.
So yeah, in practice, there's not really a hard fast rule that says if this, do this. But I will tell you, if you've got like an algebraic polynomial times a natural log, the natural log should be left alone. and we should look at the reciprocal of the polynomial. That's generally how that works with natural logs in there. And algebraic functions leave the natural log alone. Otherwise, you end up with a situation like this on the left. So let's just use that part to find our derivative. Now, another example similar to that is this algebraic times this exponential. So really, there's nothing telling us, hey, we should definitely write it where the exponential is, where we're reciprocating the exponential, or we should definitely write it as reciprocating the algebraic piece. This evaluates directly to a negative infinity times e to the negative infinity, and as x approaches negative infinity, what does e approach? E to the negative infinity approach? Zero. Remember the graph of e to the x? Here's negative infinity out here. It gets closer to 0. Or if you want to think about it, it's e over 1 over e to an extremely large number that approaches 1 over infinity, which approaches 0. However you want to think of that. So two ways to write this. We can write it as x over 1 over e to the x. Or e to the x over 1 over x. So which one of those do y'all want to work first? Two? Okay. All right, evaluate the limit again just to make sure that it's of the form L'Hopital's rule applies to. The top is approaching infinity, or sorry, the top is approaching e to the negative infinity, which is 0. The bottom is 1 over infinity, which also approaches 0. Okay. So we take the derivative of the top divided by the derivative of the bottom. The derivative of e to the x divided by the derivative of 1 over x. And then what do?
Simplify and evaluate.
We simplify and then try to reevaluate. Okay, so we've got a negative x squared times e to the x. Did that help? Now we started off with x e to the x. Now we have x negative x squared e to the x. So that didn't improve our situation because you still have this thing as an indeterminate product. Sorry, 0 times infinity. When you rewrite as, function divided by the other one's reciprocal, you should come up with something you can evaluate. If you end up then with another indeterminate product, more than likely you should abort that and go to the other way to rewrite that. It's not always guaranteed, but I think it's a good general rule of thumb. So then, you know, this thing would just keep, we're just stuck in this infinite loop with this one here. All right, the other way, when we have x over 1 over e to the x, before we do anything with that, let's just rewrite it as x divided by e to the negative x. No harm in doing that, it's still a quotient. As x approaches negative infinity, we have negative infinity on top, and what on the bottom?
Positive
Infinity, right, positive infinity. So that's still something we can apply L'Hopital's to directly. So then we're going to apply that rule. Derivative of the top is 1. The derivative of e to the negative x is negative, chain rule, negative 1 times e to the negative x. So we simplify that as what? What does that simplify to? Sorry. What was that?
So negative e to the negative x to the negative 1?
Yeah. So yeah, the negative exponents just means that it's in the wrong part of the fraction. So it's still a negative 1, but we'll put that upstairs and make the exponent positive. So you can think about it as 1 times e to the x divided by negative 1 on the bottom, but it's negative e to the x. So what is the limit as x approaches negative infinity?
Negative infinity.
Is the power on e, right?
infinity.
0, right? Why is it 0?
Oh,
Is 0 is the only thing one can't be.
I mean, I guess we could have left it alone, but our process to be consistent, we do want to simplify after we apply L'Hopital's rule. That's negative 1 over something that's getting larger and larger. So the quotient gets smaller and smaller. All right, and again, that means the original limit is also 0. Does anyone have any questions? The second indeterminate form was infinity minus infinity. So this is from the limit f of x minus minus g of x. But a lot of times it's not, it's a bit misleading to say f of x minus g of x if we don't think about f and g as both quotients themselves. So the way this arises more so is, I guess in a general sense, it would be like h of x over w of x minus, I don't know, a of x over b of x. So something, I mean, it doesn't look very user-friendly, but typically this is what you have. You have this quotient minus another quotient is typically how these forms arise. So in order to rewrite this quotient minus this quotient as a single quotient, what would we need to do there? Yeah, so this situation, typically infinity minus infinity arises from these functions where you can obtain a common denominator and express it as a single fraction. So find a common denominator to rewrite as a single quotient. That's typically the strategy here for the ones we see anyways. Okay, so for example, evaluate the limit as x approaches 0 for cotangent x minus 1 over x. So we just first need to see what it is. Just don't assume that it's, oh, it's a minus here. This is definitely going to be infinity minus infinity. Actually need a little bit of work. So the minus 1 over x as x approaches 0, that will approach infinity. What about cotangent? What does cotangent approach as x approaches 0?
It would be undefined.
Yeah, in the sense that it is
A cosine over sine.
cosine over sine. So we want to think about that as cosine over sine. What does cosine of 0 over sine of 0 approach? 1 over, yeah, and undefined in the sense that the denominator is approaching, sine 0 is approaching 0 itself, right? So this is really 1 over something that's getting smaller and smaller. The quotient cosine over sine, though, is getting larger and larger. And so that's something larger and larger minus something that's getting larger and larger. If that cotangent happened to evaluate to like 5 or 1 or whatever, then we just have a limit that's 1 minus infinity, which is still minus infinity. And kind of evaluating that directly gives us insight as to how we want to rewrite cotangent, because we've got to get a common denominator between cotangent and 1 over x. So we're just going to rewrite this algebraically. So we can combine these two fractions.
Cosine minus sine over x times sine squared x.
So sine squared, though, what's the common denominator here? It's just x sine x,
Oh,
right?
yeah, that's right.
So what is the top?
X cosine x minus sine x.
Right. X cosine cosine x minus sine x, just cross multiply. So it doesn't really look that much better, right? It actually looks a little bit more complex. Let's see what this limit is when we evaluate it directly. So by direct substitution, we have 0 times cosine of 0. That's 0 minus sine of 0. 0 times sine of 0 again is 0. So you have 0 minus 0 over 0, which is 0 over 0. So it doesn't look better, but at least we can apply L'Hopital's rule to the x cosine minus sine over x sine. Is everyone okay with what we've done? L'Hopital's rule would not apply to this directly, so don't just take the derivative of cotangent minus the derivative of 1 over x. Be a completely different function then. So maybe let's take this off to the side. We've got to find the derivative of the top. So we've got to compute the derivative of x cosine minus sine for the top here, and the bottom x sine x. Remember, we don't want to split this up. Like if we split it up, then we're right back to where we started with something that L'Hopital's doesn't apply to. So we literally want to leave it as it is, just that numerator and that denominator. Okay. So we have the derivative of x cosine as a product minus the derivative of sine. So we have the first times the derivative of cosine. What's the derivative of cosine? Negative sine. First times the derivative of the second, plus the second times the derivative of the first.
X sine x plus cosine x.
Yeah, and then minus the derivative of sine.
So it's just negative x sine x.
Right, and those just cancel out. Equals 2. So that derivative is just negative x sine x. And the derivative of x sine x, then product rule again. First derivative of the second minus the second times the derivative of the first.
That'd be plus, right? 'Cause
Yeah, it should be.
Oh, yeah. Yep, first plus second. So there's the derivative of the numerator, and there's the derivative of the denominator. So by L'Hopital's rule, then this limit was it negative x sine? Yeah, negative x sine x divided by derivative of the top over the derivative of the bottom. There's nothing we can simplify. We can't factor stuff out. So it is already simplified. And then we reevaluate. Can we reevaluate the limit?
It's 0 and 0.
Let's see what it is. The top is clearly 0. The bottom is
0 plus 0.
0 plus
0 plus 0. So what now?
Just keep going down the rabbit hole.
Do it again.
Inception, this thing.
Yeah. Do it again.
So fun.
I need to move this. Just put our derivatives down here.
It's the same.
Okay. Guess we'll use, what colors do we, what is this color?
I like that.
Is that a pleasing color?
That is a very pleasing
Yeah.
color.
All right, we'll use
I-
that
I
one.
like it, it's different.
All right, so we'll do that one for the numerator, and then we'll do this one for the denominator. Negative x sine x.
What?
Derivative of negative x sine x. We can take the negative out if you want. Yeah. So we already computed x, the derivative of x sine x here, and this is just the negative of that. Okay, so there's the derivative of our numerator. And compute that one. Derivative of the denominator, x cosine plus sine. So we kind of computed that one, but not really. We had a minus sign here. So we had a first derivative of the second plus the second times the derivative of the first plus the derivative of sine so there's the derivative of the bottom, and we'll call that however. We got two of those. So there's derivative of the top, derivative of the bottom. We'll come back to that here. Since we're taking the derivative of the top and bottom again, it's another application of L'Hopital's rule. And I'll go back down. Minus cosine, sorry. Oops. Not.
Two, right? What? Oh, here.
Is that right? X sine minus x sine cosine, yeah. All right, there's nothing we can really simplify. There's no common factors up top and bottom. So it's simplified. Reevaluate the limit. What happens when we reevaluate?
So 0 over 2.
Yeah.
So I feel like not much further.
Yeah. The top is still 0, but the bottom is 0 plus 2, 0 over 2, which is
0. We got it done.
yeah, and then we see stuff like this, and then we appreciate computers a lot more.
I would have saved so much more room had I known about this.
I mean, the point is like most of you on your job or you're not going to be doing these things by hand, right? You're going to be doing whatever. You're going to be using a computer of some sort.
We're calling the programmers when it doesn't work.
Yeah, right. And some of you that are software engineers need to know this, but most people don't, right? Like software engineers need to know how to program a computer to compute this. Most of us don't, but it's the process of like learning how to think about something differently that hopefully is like opens up neural pathways that you don't have currently. So if nothing else, to take that away. I know it seems like a cop-out, but isn't that the whole point of intelligence and learning? Is expanding your mind? I think. Maybe you don't.
Yeah, it's just.
Okay. Questions on that?
Sin x plus cosine x.
Okay, then the third indeterminate form. By far the most lengthy of the three processes.
Is this one?
Is this one.
Great.
But what you'll see is that this does relate back to the first situation, the 0 times infinity.
Isn't 0 to the 0 power technically 1?
In certain situations it
But
is.
in this one, we're not doing that.
Not in the sense of a limit, yeah.
Okay.
Like, if you're like, you know how you expand a binomial like this? Depending on what that power of n is, the binomial theorem, it's just expanded this way. Like, one instance where 0 over 0 has to be 1 is when you use the binomial theorem to expand. Otherwise, it's not a valid formula. So 0 over 0 has to be 1 in this situation, but this situation doesn't involve a limit. So in the sense of a limit, 0 to the power of 0 is not defined. Or it is defined, but it could be anything. And again, just a reminder, these come from limits that are f of x to the g of x. So how did we deal with f of x to the g of x? How did we rewrite that? Came up when we were doing derivatives. One way, if we had a function to another function, to take the derivative, we said we could use logarithmic differentiation, or we could rewrite it. Yeah, so remember it's just e to the ln of that thing. Right, and then by properties.
Is a coefficient, a front coefficient.
E
Yeah,
to the g of x times f log f of x.
yeah. So that we rewrite as e to the power of g times ln of f. We'll just say which is equal to. It's right here. Let me see how much space I have. Okay. So notice if we rewrite this way, then we're actually just computing the limit as x approaches whatever on e to the power here. So that's actually what we want to work with. But if we think about, like, for instance, the 1 to the infinity, where that's coming from, it has to come from f approaching 1 and g approaching infinity. Right? In order for this f to the g to be 1 to the infinity, f approaches 1, g approaches infinity. But then when we look at it this way, if f is approaching 1, then that's the natural log of 1 times g, which is approaching infinity. What's the natural log of 1? 0. So this is actually e to the power of 0 times infinity. Similar situation if f is approaching 0 and g is approaching 0, Then it's 0 times the ln of 0, which is 0 times infinity. And infinity to the 0, f is approaching 0, g is approaching, or sorry, f is approaching infinity, g is approaching 0. But in the g of x times the ln of f of x power, it again is another 0 times infinity. So all three of these, when we rewrite them, boil down to e to the power of 0 times infinity. That's why those three are indeterminate, because they're really the indeterminate product that we looked at before in disguise. So that's what I said here. These limits will always relate back to 0 times infinity. So to compute the limit as x approaches a of f of g of x, when it evaluates to one of those three forms, we're going to rewrite f of f to the g as e to the g ln f. That limit doesn't operate on e, it's only operating on x, which is in the power. So then we're just going to put that limit into the power and then start the process of computing the indeterminate product like we did in example 1, 2. So once we have it rewritten, we then just reevaluate this case here like this, and then we end up with some limit for this thing right here. But then the overall limit is actually e to that power, is e to the L. So that's what we kind of spelled out there. Yeah, right. So I mean, it's a pain, but what you see is it's not a trivial thing to evaluate limits, even if it's, you know, something that's like 0 over 0. It's not straightforward always. So it's very difficult. So you just got to remember what happens here a lot of times is there's so much work involved in just computing this limit here that people forget that it's actually e to that limit as the final answer in those three cases. So that, hopefully that makes a little more sense if we actually look at an example. So we'll start this, we won't be able to finish it. But if x is approaching 0, then we have, by direct substitution, this is 0 to the power of 0. So whenever that happens, you first want to rewrite, we want to rewrite x to the x as e to the x times natural log of x. I'll just write it over here too. X to the x is e to the natural log of x to the x, which is and then really all you're computing here is e to that limit power, e to the limit. Is everybody okay with that? So really that first step is nothing but an algebraic step using inverse properties of e and natural log. And we've actually already computed that limit, x ln x as x approaches 0. So just for time purposes, we'll say for this limit here, see example 1, we had that limit come out to be 0. So this limit x to the x is really e to the power of 0, which is 1. We'll see another example, we'll work all the way through, but that's the basic idea to evaluate those. Of course, x to the x is the absolute simplest case of those. When we come back, we'll look at a different one. Do y'all have any questions before we go? Oh, no, I didn't. Everyone was here today. All right. Well, have a good weekend. I'll see you all Tuesday.
My dad wants me to try to figure out.